Hey there, I'm David. If you've ever had a linear algebra class that's at all interested in applications, you've probably seen an example that's something like this. What happens here is you start with an image, and then you compute a low-rank approximation of that image using the singular value decomposition. The point of this video is that there's a better way to do this type of approximation. It's even better than the SVD. And guess what? It even uses the SVD. Let's back up a second. What is the SVD? The SVD is a matrix decomposition. What this is it takes an input matrix and it identifies the orthogonal subspaces underlying the row and the column space of the matrix. If you've had a linear algebra class, you probably know what that means. If you haven't, don't worry about it. What this basically means is that it identifies the fundamental frequencies of the matrices. Back when we used to have radios, it would be like tuning a radio. Anyway, what this does is it just finds the most important directions inside that matrix, the most important vectors. One of the reasons the decomposition is so useful is because of the best low rank approximation property. This was originally noticed in the 1930s by two fellows named Eckert and Young, and then later improved in the 1960s by a fellow named Mirsky. The best low rank approximation theorem is important because it gives us an ideal way to represent a matrix with fewer numbers. So here's a 10 by 12 matrix. If I were to write this out, as I've done on the screen here, we need 120 numbers. But I've hidden something in this matrix. This matrix is really a rank 3 matrix. So I really only need a rank 3 approximation, which means I need 3 row vectors and 3 column vectors in order to approximate it. If you add up those two numbers, those 3 column vectors give us 36 numbers, and those 3 row vectors give us an additional 30 numbers. So I can represent all 120 numbers with just these 66 values in the rank 3 approximation. It gets even better. What those three fellows showed is that you could approximate a matrix as best as possible with the low rank matrix. This is sort of like what your computer does when you save a JPEG image. It actually throws away a lot of information in the original image, but it's designed to approximate it such that you really don't notice a difference. What those three fellows showed is that the singular value decomposition has a similar property. It shows the optimal way to throw away information in a low rank representation such that you get the best possible result. Simply put, Eckert, Young, and Mirsky's result showed that you can't do any better than the SVD approximation if you want a low ranked representation of your matrix. Except you can do better than the SVD using the SVD itself. How does this make any sense? Well, you have to remember that Eckert, Young, and Mirsky all wrote about approximating a matrix. And now a matrix is a coordinate-wise representation of a linear operator. But what we're talking about is approximating data. And there are many ways of associating data with a matrix, or correspondingly representing that data as a linear operator. For instance, here are two examples of the same data, but represented as two different matrices. One of these matrices is rank 1, and the other is rank 4. So the order or the way you put your data into a matrix matters for the representation that we're going to get when we apply the Eckert, Young, and Mirsky result. Getting back to images, normally we think of the matrix associated with an image based on the pixel grid of the picture itself. We think of this as pretty natural. But it turns out that there's a better way to represent it as a matrix. Picture instead a matrix as a set of small little tiles. Now, what we're going to do is we're going to take each of these little tiles, each of these little pieces of the picture, and we're going to extract them out and treat each tile as its own little vector. So we're going to take the pixels in each tile and we're going to string them out into a big long column vector. Then we're going to append all of those column vectors into a big long matrix. That's a different representation of the same data. We're still storing the same information. We could extract the same type of representation, but we've totally changed the type of linear operator and the matrix that we're looking at. We call this approach a matrix of tiles. Now, we can run a low-rank approximation on the matrix of tiles, and it turns out for a lot of images, we get a better representation than we get from using the SVD on the original image. It is both lower parameter and higher accuracy. Here's that picture from the start again. Which of the two approximations would you prefer? And that's how we can do better than the SVD using the SVD itself. Let me jump into academic mode for just a second. What I'm really talking about here is what we would call a Kronecker product SVD. The improvements possible with this tiled or Kronecker product structure were first noticed by a fellow named Charlie Van Loan and co-authors around 1993, and they wrote a paper about Kronecker product structured problems. More recently, there was another paper called COPA, or Kronecker product approximation, that noticed the same type of structure. And that's the first time I think I've ever found an instance where this tiled approximation being better than the original image was noticed. But just speaking more generally, people in deep learning or convolutional neural networks have for quite a while now used tiled approximations of images as a fundamental primitive in a lot of the deep learning pipelines. And going back even further, this is actually how JPEG compression works. JPEG compression starts by taking your image and representing it as 8 by 8 pixel tiles. So with this, I just hope you remember that when we talk about having the best approximation for the SVD, we're talking about the best approximation of a matrix, not about the data inside the matrix. So remember that you can oftentimes get much better approximations if you think carefully about how to represent the data inside your matrix. Then the SVD can do even better than just taking simpler, straightforward approximations of the original data. Have a happy leap day. Happy 23rd birthday, Gene.